Hello everyone, welcome industrial students and vertical flight enthusiasts to today's webinar. Thank you for joining us, most of you on your lunchtime. Since our past few events have been more industry driven, we thought that today we would focus more towards academics and their impacts on the vertical flights community, especially within our ecosystem in the extended Montreal area. Today's presentation will be about collaboration that exists between industries and academics. We'll be showing successful collaborations examples for three different domains: aeroacoustic, additive manufacturing, and rotor icing. So for a brief overview of our chapter, trying to switch the slides. Okay, so the Montreal-Ottawa chapter, you can see the current roster on the slide here, with our McGill University chapter at the bottom. Vertical Flight Society was previously known as American Helicopter Society and was founded in 1943. The Montreal-Ottawa chapter was founded in 1987, so we are celebrating our 35th anniversary this year. VFS mission is to increase the interest in vertical flight across Canada to create a platform to facilitate networking and collaboration, and also to provide learning opportunities through exclusive conferences. So if you want to be involved with us, you just have to join us and or call us and reach us any way that you want, and we'll be happy to help you join the community. So for today, the presenters, we are honored to hear from our three distinguished guests who are very heavily involved in the vertical flight community. They're all leaders in their respective field and have led ambitious projects with industrials. First, we'll hear from Stéphane Moreau from Université de Sherbrooke. Stéphane got his PhD in mechanical engineering with a minor in aeronautics and astronautic from Stanford University in 1993. He then worked at the turbo engine supplier SNECMA from the Safran Group, and later in an automotive supplier, Valeo, on engine cooling fan system design. He joined the mechanical engineering faculty of Université de Sherbrooke in 2009. His research topics include aeroacoustic, turbo machinery design, and CFD. Before this meeting, I was looking at his numerous scientific publications on the web, and I stopped counting them at 300, so that's quite a large body of work. Our second speaker will be Eric Villeneuve. Eric received his PhD at the Université du Québec at Chicoutimi in 2020. He is a sponsor of SAE AS 5900 and did several technical revisions of the document. He is a member of different icing committees like the SAE G12. Since 2011, he performs and manages research projects on atmospheric icing, heat transfer, and vibration at the ANSI Icing Materials International Laboratory. Eric is also actively involved in industry university collaborative project on icing, and in particular rotor icing. I recently visited Eric in Chicoutimi for a project with them, and I can say that they have very impressive facilities and research teams. And finally, last but not least, we'll hear from Mathieu Brochet. Mathieu got his PhD in 2003 from McGill University. He then worked at NRC Aerospace Manufacturing and Technology Center on electron beam welding and freeforming of aerospace materials. He then accepted a postdoctoral position at the Advanced Materials Laboratory of Sandia National Laboratories. Late in 2004, Mathieu started his academic career at McGill University and is now an associate professor in the Department of Mining and Materials Engineering. His research activities are focused in three areas: powder metallurgy applied to nanostructures material, rapid solidification welding processes for joining and freeforming of nanostructures materials, and energy-related materials. Mathieu now leads the Laboratory for Powder Processing and Additive Manufacturing of Advanced Material at McGill University. And now I already stole valuable time from the speakers, so let's start our feature presentation. Please feel free to write questions in the chat. We'll try to answer them all at the end. I'll now invite Stéphane Moreau to present his work on aeroacoustics. Stéphane?
Thank you, Maxime. Welcome, everyone. So let's go to the next slide right away. So where are we? Actually, yeah, thank you. So we are in Sherbrooke, so it's 150 kilometers away from Montreal. And if we click again, and we basically our campus is a nice campus over here in the forest, and you see my office there. So next slide. Who are we? So we are the Aeroacoustic Group, part of the Crash Research Center at UDS. It's a group of about 20 people. Currently, we have 1 research associate, 2 postdocs, 12 PhDs, and 4 masters and several interns. And they are from all around the world, as you can see actually from the left picture. And we cover analytical, numerical, and experimental aeroacoustics of propulsions and ventilation systems. And I would say all main noise sources of transportation systems, from cars, railways to aircraft. And we, as I said, we have a nice experimental facility. So this is in the next slide, please. So if we start with the acoustic experimental capabilities, we have a couple of reverberant and anechoic rooms first. Then we have a unique, very low turbulence level anechoic wind tunnel, so very quiet wind tunnel. We have a PIV laboratory, a supersonic blowdown facility that you see at the bottom right. And we have basically skills in different experiment fields, like far field noise, wall pressure fluctuations, hot wire anemometry. We're able also to do some flow visualization from Schlieren techniques all the way to tomographic PIV. Now, in terms of numerical expertise, it goes from RANS to LES to DNS, and you have an example at the top right, and using both Navier-Stokes and Lattice-Boltzmann methods. Now, in terms of analytical expertise, we have a long-term research on analytical modeling of airfoil, fan, and turbomachinery noise over 20 years. And this is in grand part due to a very strong industrial partnership, excellent relationship. For example, I had like 3 different industrial chairs with different aerospace partners. So next slide, please. And this all for dealing with aeroacoustics. So what is aeroacoustics? Aeroacoustics is basically the noise coming from turbulent flows, in contrast to vibroacoustics, where it comes from the vibration of structures, for example. So as we are dealing with turbulent flow, we can basically decompose this turbulent flow in gust. And this is basically the sketch I'm showing on the left. So this is my blue gust here hitting a profile or rotor blade. And this will create an unsteady loading on the blade, which are equivalent sources. So this is the red part, and this will be propagating to the far field as acoustic wave. This is my green part. And you can do that in these 3 different steps, starting from a very simple basic methods analytical approach all the way to fully numerical, so the direct approach. And of course, it's with increasing computational cost. Now, in the case of the direct approach, we simulate everything. We simulate the sources, but also the propagation. But still, we are limited usually to near field, so we need to do some kind of propagation with the porous Fox-Williamson-Hawkins analogy, for instance. Now, if we want to be a little bit cheaper, we can use an hybrid approach where we basically resolve the aeroacoustic sources, so in the source region, so in a limited domain, and then we'll propagate again with a propagator, which can be a linearized Euler solver or acoustic analogies. And in my group, we use mostly acoustic analogies, as I will show later. And then the simplest way is to do all the 3 steps analytically. And this has been, I think, one of the key thing of my group, basically to use these analytical models and to combine them with RANS. And this is what I'm going to show basically in the next slide. And the advantage there is we can separate the noise sources. So next slide, please. So if we do that, so we start actually from RANS simulations that are used for performances prediction. So what is being done, I think, regularly in industry, and then we feed that in some source modeling, analytical source modeling, that will be basically the sources for then the analytical aeroacoustic models, which are basically, again, Fox-Williams and Hawkins or acoustic analogies in frequency. And this will basically allow to predict tones and broadband. And we've basically developed, I would say now, a commercial code, a commercial software called OptiSound that is being commercialized by Optis. And you can find basically more detail on that in the website that is at the bottom right. And this is for only axial machines, as I show here. Next slide, please. Now, if we move on to the different projects, a first project we achieved in aerospace was to basically do realistic jet noise prediction. And you see at the top that we were basically able to simulate complete dual stream nozzles like you have, for example, in the scale CFM56 that we show on the right. So this is an experiment that was done at Onera, and we reproduced basically the experiment in simulation. And this is the top picture where you see basically the turbulent jet with the acoustic field coming out from the jet. And we validated that with some measurements, some PIV measurements for the aerodynamic part, and then with some far field acoustic measurements, directivity measurements. And we have good flow and far field acoustic prediction. And on top of it, we provided basically an industrial tripping methods to be able to achieve that. And you see that at the top right. Next slide, please. The second project is basically the prediction of the noise of high lift devices. Again, we started by predicting basically the flow correctly, and this is what is shown at the top with the 3-element L1T2 configurations. And you see, for example, the pressure distribution on the main element that was well predicted. And then we went on basically with a large eddy simulation to predict basically the noise sources and then the far field. And this is what is shown at the bottom. So you see the noise sources, the turbulent eddies grazing along the plate and then interacting with the flap. And you see the noise generated on the right with the different interaction actually between the two elements. And we were able to predict basically interactions of profile flap in this case, but also slat profile and consequently the noise. And we have also developed an analytical model for flap noise with diffraction effects. Next slide, please. The third project is the transonic outflow valve noise prediction. So the valve, the transonic valve, the OFV, is actually what pressurizes an aircraft, and it's usually located at the end of the aircraft. We've built a test bench. This is my blowdown, supersonic blowdown facility that I showed previously, where we perform Schlieren and pressure measurements. And then we perform basically the simulation of this facility, both with RAN simulation and then with LES. And the LES, you see the prediction actually on the right, in the middle right, where you see the noise source prediction and then the consequent also noise propagation. And at the bottom, you see basically a Schlieren picture of the experimental part. And we were able basically to identify the noise sources at various flow regimes. Next slide, please. Now, the first, I would say, ducted rotating machine or turbo machinery noise prediction was done on a high pressure turbine. So we did some large eddy simulation of the MT1 transonic turbine with and without injection of entropy and acoustic waves. And you see actually at the bottom left, the clean prediction where you see the complex flow, particularly all the shock waves that are present both in the stator and the rotor rows. And on the right, you see the equivalent thing with the entropy, plain entropy wave injected at the inlet. And this allowed us basically to identify again the noise sources for indirect combustion and high pressure turbine, and to show, for instance, that the dominant indirect combustion noise is produced in the first row, and that a little bit of reflection is done towards the combustion chamber, but most of it is transmitted. Next slide, please. The second ducted turbomachinery noise application is the NASA SDT turbofan, which is the AIAA benchmark. So we did again several large eddy simulations of the rotor OGV configuration and also of the rotor going all the way to wall resolved LES in this case. And on the right, you see basically the predictions, acoustic predictions, both the upstream and downstream sound power levels, compare basically to the measurements that were achieved at NASA. So the gray and black curves are basically the measurements, and the blue is actually our free field prediction, and then the red ones are basically our annular duct analogy, Goldstein annular duct analogy. And you see that using this analogy, we have a good overall prediction. And if you look also at the structures that we see in the LES, we have basically proven that we have a transitional regime in both rotor and stator at approach. Next slide, please. Now moving to open rotors, which is probably more of a concern of this society. We first looked at propeller noise prediction for civil aircraft and electrical civil aircraft. And this is an example of project achieved with Optis, where basically we did the measurements, so outdoor measurements at the Sherbrooke Airport during the winter. So you see basically the setup. And then we did some prediction using basically OptiSound. So we did first the RAN simulation that you see in the middle to show that we have like these two major, I would say, secondary flow, which is the tip vortex and the corner vortex at the hub. And these turbulent structures are basically responsible for the broadband noise that we've been then predicted with OptiSound. You see the dashed black line on the right compared to the experimental orange spectrum. And you see that we are matching quite well, actually, the all high frequency part. And then we added also some tonal noise prediction, so thickness and steady loading. And you see that we are predicting also nicely the first tones. Next slide, please. The next application is a more, I would say, up-to-date or contemporary application, which is an urban air mobility case, where we have a large ducted fan that you see on the left, and we did experiments in the UDS anechoing chamber, where we did the measurements shown at the bottom. So we did directivity measurements, and you see basically the experimental measurements in pink and red. And then we performed high fidelity hybrid LBM VLES simulation of the whole setup on 3 different grids, so that we had like grid independence. And you see basically the final simulation on the right, where you see these very complex tip vortices formed at the blade tip, interacting actually with all the blades. And this is what is creating actually the large fluctuations of pressure, mainly at the tip, that we see at the bottom right. And then when we look at the direct noise prediction here, it's a direct noise prediction in black. You see that we are able basically to predict not only the broadband hump, but also the tones and also the subharmonic humps, the subharmonic humps that are just before all the harmonics, the tonal harmonics. So we're able to do VLES source localization, plus a good OptiSound noise prediction also on the side. So moving to the next slide and the final application, final project, we also did some helicopter noise prediction. And these are basically the first, I would say, LES simulations of the UH1 reference blade in 2 different flight configurations. On the left, it's in over, and on the right, it's in descent, so in an approach condition. So we have flow coming from the left. And you see that in both cases, with this dilatation field, we see actually that the acoustic is generated at the blade tip, and it's much stronger, of course, in the approach condition on the right than on the left. But again, this is also due to the same thing. We still have an interaction even in over, and this is shown at the bottom left. We still have a little bit of interaction with the tip vortex generated by the tip blade with the consequent blade. And this is basically the LES has allowed us again to do a good source localization. And now we have fed all of this either directly in the share FWH, so the Fox-Williams-Hawkins analogy code, or to the OptiSound with both RANs and LES inputs. And this is basically the comparison of the prediction. So in red is the direct LES prediction, and the dashed lines show you, actually green and blue, show you the prediction for the broadband component. And this allows us to basically show that at mid-frequency, really what is causing the hump is interaction of the tip vortex, whereas at the high frequency, it's mostly the trailing edge noise coming from the turbulent boundary layer developing on the blade. Now, in terms of tones, we're also able, with the prediction of thickness and loading, to get also the tones. So good OptiSound noise prediction. So next slide. So if I conclude, these are all for the projects. We've been able to perform several computational aeroacoustics results in complex geometries, combining both hybrid and direct noise simulations. And I would say that basically the third golden age of aeroacoustics has started. We've been able to deal with more complex, realistic geometries, and we have been able to consider even, I would say, the test setup, especially with the lattice Boltzmann method. And the high order schemes on unstructured grids have provided results for all types of jets, and now high-speed turbomachinery and outflow valves. Now, the physics-based analytical models, as implemented in OptiSound, combined with RANs, also provide, I would say, an efficient pre-design noise prediction, possibly that can be embedded in optimization process. Now, our objective in our partnership with industry is really to provide new insights in noise mechanisms and source localization, develop and validate new acoustic methodologies, and also test new methods and develop new models to be integrated in early design. And finally, the key to success is, of course, a close and confident collaboration, and also for us, the ability to publish, because it's an answer requirements to get funding. Thank you very much.
Thank you very much, Stéphane. It was a very interesting work. Now we'll move on to Eric.
Yes. Hi, everyone. My name is Eric Villeneuve, and I'm here to present you the drone rotor icing investigation that is going on at the lab at the moment. Next slide, please. First, I'm going to do a very quick explanation of the Anti-Icing Materials International Laboratory. So we are in the Icing Research Lab attached to the University of Quebec at Chicoutimi since 1987. And we study icing phenomena and cold climate related problematics for various industries like the aerospace and the energy industry. We are also the only laboratory in the world accredited to perform the aerodynamic qualification of anti-icing and de-icing fluids for aircraft ground de-icing. And we are accredited by the Performance Review Institute of the SAE to do that. Next slide, please. We have two refrigerated wind tunnels, so a research tunnel capable of simulating icing precipitation with wind speed up to 100 meters per second and temperatures below -20 Celsius degree. And we have a second tunnel which is dedicated to the qualification of aircraft ground de-icing and anti-icing fluids, in which we simulate the takeoff of a Boeing 737 Advance to measure the effect of those fluids on the aerodynamic performance during takeoff. Next slide, please. We also have 6 cold rooms capable of reproducing different types of precipitations, freezing rain, freezing drizzle, snow, ice pellets in highly air control conditions. We have one -60 Celsius degree cold room and 2 cold rooms more than 9 meter high for different testing. Next slide, please. So today for this presentation, I'm going to mainly discuss the overflight icing tests that were done on the APT-70 drone rotor at the laboratory. So this drone is a drone that has a vertical takeoff and then transition into aircraft mode for forward flight. So there was 3 main objectives for this project: the development of the experimental apparatus, a preliminary investigation of the icing effects on the rotor performances, and also preliminary tests of ice protection solutions. And I'm going to briefly talk about also the forward flight wind tunnel testing that is to come. Next slide, please. So the first objective for the overflight test was to develop a new experimental apparatus and to define the icing conditions in the cold room. Next slide, please. So we installed the rotor in a 9 meter high cold chamber where the air temperature can be controlled between -35 and 5 Celsius degrees. We have icing nozzles located on the chamber ceiling to generate an icing cloud. The icing test section has an area of 2 meters per 2 meters, surrounded by plexiglass doors. And the rotor was installed on top of a pneumatic cylinder, which can be extended vertically using compressed air to test at different heights. So different distance from the ground, different distance from the nozzles. Next slide, please. To define the icing conditions, we use the FAA AR0945 documents because we wanted to test both freezing rain and freezing drizzle precipitations. So for the freezing drizzle, we went with the droplet size of 120 microns, while for the freezing rain, we increased the droplet size up to 800 microns, so very large droplets for precipitation. And temperatures was selected were -15, -12, and -5 Celsius degrees. Next slide, please. For the rotor test conditions, we went with an 81% scaled down version of the APT-70 drone rotor. So 4 blades of 25 centimeter long for a total rotor diameter of 66 centimeters. And we decided to test 3 different thrust levels, so low, medium, and high thrust. So for the scaling rule, we went with 2 different scaling calculations. So the same centrifugal force and same tip speed. So for each thrust level, we had 2 corresponding RPMs for a scaled down version of the rotor. So we did not test 4,300 RPM because it was too close to the 4,400 RPM. And we did not test the 5,500 RPM because it was too close to the electrical power consumption limit of the motor used. Next slide, please. So during testing, we record different data, different parameters like the rotational speed, electrical power, the thrust, and torque. And during a test, so what we do basically is we start the rotor, we slowly increase the RPM until we reach the target RPM for the test. And then, as you see on the plots, we initiate the icing spray in the cold chamber, and then ice accumulation begins on the rotating blades. So as you can see, the electrical power will start to increase to maintain the a fix, because the testing is done at a fixed rotation speed, so at fixed RPM, the electrical power will increase to due to the ice accumulation on the blade. And you can also see the torque increase and important thrust decrease during the icing events. And then once at some point there's going to be a shedding of the ice on one or more blades, and then the vibration levels will increase due to the imbalance, and we will reach attain vibration above the safety limits given by the manufacturer. So we have to stop the test at that point. And we use also for the analysis non-dimensional coefficients, so the thrust coefficient and the torque coefficient. And you can see during the test in real time the percentage of thrust coefficient losses and torque coefficient increases. Next slide, please. So the second objective was to investigate the impact of different test parameters on the rotor performances. Next slide. So first we looked at so here you can see some examples of the 3D scans of the ice accumulations that we made. Also pictures of the evolution of the ice accumulated on a blade during a test. Next slide, please. So the first parameter that we looked at was the effect of the droplet size. So we observed that the degradation of the performances were far more important for the larger droplets. So as you can see on those plots here, with the black line showing the droplets of 120 microns compared to the blue line, which showed the 800 microns. So you can see a much faster degradation. Just for example, the red line shows that for the droplet with 120 micron, you need 5 times higher precipitation to reach similar degradation. And this faster degradation is obtained due to the faster ice accumulation on the blade, so higher accumulation rate with the large droplets, and this could be attributed to their higher inertia. So the larger droplets are less likely to follow the streamlines around the airfoil due to their higher inertia, and then impact on the leading edge instead of following the flow around the airfoil during rotation, like the smaller droplets will have a trend to do. So it's basically caused by a different collection efficiency of the blade. Next slide, please. And this seems to be in line with the accumulations observed towards the tip of the blade. So you see 2 examples of ice accumulations with the 2 different droplet size. And we see that the tip of the blade, the effect of the tip vortex, which is a lot more pronounced with the smaller droplets, being more impacted by the flow surrounding the rotating blades than for the larger droplets. Next slide, please. Then we'll look at the effect of the air temperature. So the first thing that we observe is that more of a glazed ice was obtained at warmer temperatures at -5 Celsius degrees, so a clear glazed accumulation, while for the lower, colder temperatures, we obtain more of a hard rime accumulation, more of a white ice. Next slide. So for the air temperature, so for the droplets of 120 microns, the decrease of air temperature did not generally affect the outcome of the icing test. So even if the ice accumulation, the ice type was different, the performance degradation was similar between the different temperatures, and it was similar to observation also made by experiments at the NRC on also overing UAS experiments, as you can see on those pictures. So it was consistent with their results as well. However, next slide, please. When we looked at the results for the 800 micron test, we saw that at lower temperatures, the degradation of the truss was far more rapid, and also the torque increased more rapidly at the lower temperatures. So you can see on the plots here the blue line for the -5, while the black lines for the -15, showing the higher degradation. And what we observe during post-treatment is that for the larger droplets, almost no ice accumulated at warmer temperatures at the tip. So if you look at the pictures there, you see that -5, there's almost no ice at the tip towards the last third of the blade as compared to -12 Celsius degrees. And what could explain this is that the larger droplets, due to higher thermal inertia, take more time to freeze and has time to be exposed by the higher centrifugal force toward the tip of the blade before they are able to completely freeze on the blade. Next slide, please. Previous slide, yeah. So the last parameter that I'm going to present here is the rotation speed that we also investigated. So you see on those plots the three different RPMs. So the black line is 38 RPMs, the blue line is 44,000 RPMs, and the red line is 4,900 RPM, sorry. And what we observed is that the performance of the rotor was less severe as the rotation speed was increased. It was also caused by a higher ice accumulation at lower rotation speed. And this could also be attributed to the effect of the higher rotation speed on the overall vortex airflow surrounding the blades during rotation. So next slide, please. What was observed is the increase in rotation speed seems to affect the overall vortex airflow surrounding the blade during rotation. So that's something that we want to go further into details. We want to study further this phenomenon. Those were only preliminary testing, but we see the evolution of the ice accumulation, especially toward the tips, as we increase the rotation speed, explaining why there's lower degradation at higher RPM. So there's much less ice, especially toward the tip of the blade. And on the pictures on the left, you see also the effect of the tip vortex on the ice accumulation is far less pronounced than for the lower RPM. Next slide, please. Then the third objective for the overflight testing was the preliminary test of ice protection solutions. Next slide. So first we tested isophobic coatings. For those who don't know what an isophobic coating is a paint or a coating that we apply on the blade that reduce the adhesion of the ice on the substrate. So the adhesion of the ice on those coating is far smaller than on the bare blade, which allow the ice to shed more quickly. So if we look at the plot, so the curve, the black curve shows the results that I have presented before. So when there's no coating present on the blade, so for the bare blades. So we see the fast and significant degradation of the performances in function of time until there's a big shedding event, and then the vibration levels increase and becomes too high, and we have to stop the test for safety reasons. With the 4 isophobic coatings that we tested, this is a different scenario that occurs. So since the adhesion of the ice on the substrate is far lower, the ice shedding events occur much quicker. So the degradation of the performances are much lower when the shedding occurs, but also there's less ice. The mass of ice is much less on the blade. So when the shedding occurs, there's less imbalance, and we are below the safety limit, and we're able to pursue testing. And what occurs then is that we get some accumulation shedding cycles that are obtained. So small accumulation, then there's shedding, the performances re-increase, then there's a accumulation is pursued, so the performances decreased again until another icing cycle and so on, and we can almost pursue testing indefinitely for those cases. So so it means that the rotor could sustain those kind of icing with the coating present, while also only tolerating some slight performance losses during the icing events. Next slide, please. We also investigated the electrothermal protection. So we install heating elements on the blades. We cover with the aluminum tape for a more even distribution of the heat on the blades. We install RTDs at different positions to measure the temperature. And then we ran multiple tests at different icing conditions in anti-icing and de-icing mode. So in an anti-icing, you completely prevent any ice from accumulating, while in de-icing, you allow a certain amount of ice before you turn on the electrothermal protection. Then the ice shed because you melt the interface between the blade and the ice layer, and then you shut it down again, and you wait for a new accumulation before returning on the system. So the results are unfortunately still being analyzed, so I cannot present them right now. Next slide, please. So the next step in our experimental testing will be the forward flight in wind tunnel. Next slide. So this is going to simulate the forward flight of the drone in aircraft mode. So we have built a new 36 inches circular test section for the wind tunnel, where wind speeds can go up to 50 meters per second, down to minus 20 Celsius degrees. We have 25 nozzles to create the icing precipitation. We'll use a stroboscope, high-speed cameras, 3D scanners to observe and analyze ice shapes. And we perform again multiple icing tests at various conditions based on regular standards. Next slide, please. And finally, we have built a new cold room around the tunnel test sections, so we can remove the blades from the tunnel and then make all the measurements in the cold room without compromising the ice accumulation. And calibration of the tunnel is almost completed, and we will begin testing next week. Next slide, please. So thank you all for listening to my presentation.
Thank you very much, Eric, for this in-depth look at your work. I'm sure this is a test that will be very useful for the industry for future certification of drones. So our final speaker, Mathieu Brochu.
Yes, hello, Maxime. Hello, everybody. Thank you for giving me this opportunity to talk today. Within the title of this webinar, I'm going to deal with the additive manufacturing section. So we were asked to deliver on a few topics. We'll talk about 5 small topics today. So the first one, Max, please. Next slide. Okay, so the first thing, just so that we're all on the same page, what is additive manufacturing? So on the next slide, there's a small video that I like to present. To me, I see additive manufacturing is a manufacturing process where we grow part. We're not taking a piece of material that we remove to give the final shape. We basically grow it layer by layer. And if you're looking at the analogy and the two videos that are there, you can see that additive manufacturing is really similar to Lego, but for grown-up. That's a little distinction here between the two things. So despite the fact that additive manufacturing, perhaps some of you might not be aware, but date from the 1800s. So the first scanner, if you're looking into this, was developed in 1860, the first 3D printer in 1890. It's only since about 10 years old, 10 years ago, that we started to use that technology to fabricate components. So it's quite recent, and we have to develop the heritage if we want to start to use it commercially. So if we move to the next slide, we can see a few applications where now people are starting to consider additive manufacturing for fabrication of part in the aerospace application and vertical system. Among the main advantage that you can see, you have an example here from the Cobra Aero AM engine blocks. You can see that part of the engine blocks was lightweighted by the introduction of a lattice. So sort of like voids or empty space within the engine block, which reduce the weight. The additive manufacturing will allow you as well to go with design with higher complexity and part consolidation concept, as you can see on the picture on the bottom right, which is a full drone where part consolidation to minimize assembly was put together. So that's an existing one that was printed here in Montreal by Fusria Group. And we can now start to adapt the production of parts from a few parts, highly prototyped, to serial part. There are some applications where the economics of serial part can work. So if we move to the next slide, we have additional examples here that are closer to the presentation. So on the top right, you have the transmission casing from Chinook that was from a Chinook helicopter that is fully 3D printed. You have on the left an engine torque indicator that was developed by Bell Helicopter Textron Canada here to host instrument that are used. This was a titanium 6.4 component that was manufactured. And just to show you the versatility that you have on the bottom right, you have an example here of a composite 3D printed blade that is used by Bell Helicopter. So if we move to the next slide, so this is basically now moving to my research team and what do we do. So our research team, next slide, please. Our research team is currently hosting 25 researchers. So a picture a couple of years ago during our Christmas celebration, 2 research associates, 1 technician, and a series of grad students. And we're funded by over 20 industrial sponsors. And if you want to see the lab website, the address is there. So next slide, please. So these are the activities. By training, I'm a person working in welding and I've done powder metallurgy. So if you combine the field of welding and powder metallurgy together, you're obtaining 3D printing. So we're working on the process optimization, how we can fabricate new parts and how we can try to think outside the box compared to what everybody is doing. And I'm going to show you a couple of examples later on where we specialize, for example, fabrication of components with lower reservoir stress, texture control, etc. We're working as well with alloy development. The additive manufacturing field is a different solidification condition than casting and welding, so we have to think a bit differently. We're working as well on how to optimize and engineer the powder that is a feedstock for additive manufacturing. And metal powder sintering and rapid welding, which are not going to be covered for today. So if we move to the next couple of slides, these are the suite of equipment. So as I mentioned before, we have a very holistic suite of equipment to characterize and optimize powder to maximize their printability and sinterability. So we have a few examples here of facilities that are in the lab. Move to the next slide. If you will see the series of printer that we have in the lab, we mainly focus on laser powder bed fusion, the left 4 unit. We also have direct energy deposition that are possible with powder and with wire, and direct writing with extrusion. And finally, the last piece of puzzle that is missing, which is the next slide, is a series of furnaces and characterization equipment to understand their heat treatment, to optimize mechanical properties, to understand their thermal cycling, to understand their residual stress and their geometry, dimensional, and tolerance. So that in 3 slides completes the suite of equipment that we have in our laboratory. If you move to the next slide, we'll present a couple of examples that we've done with aerospace companies. So next slide, please. So as I mentioned before, 3D printing really started, if you're looking at the commercial adoption, about 10 years ago at most. And the goal is to develop heritage. So in our lab, we are working with a very large consortium on various projects to try to demystify and understand what are the real capabilities and how we can improve the process. So we really need to create the story on the process, the applicability, the mechanical property, reliability, etc. Therefore, a lot of companies typically bonds together or collaborate together to reach those examples. It's less risky for them than go along in this adventure. So if you move to the next slide, we're going to see 4 examples of parts that we've done. That we have published. So the first one here originates from a CREAC program a couple of years ago. This is a large-scale aerospace structure that you can see here. So you have the CAD model that is on the left, and the final model that is 3D printed that is on the top right of the slide. So we fabricated the entire component. This was qualified from TRL2 to TRL7-8. I would say the part met the specification and was ready to launch. At the beginning, when this part was fabricated, it had a buy-to-fly ratio of about 31. And now with the 3D printing, within 2.5 days, we managed to bring this part into a buy-to-fly ratio of 3.2. So you can see the sequence here that went through, where we fabricated the bulk of the part. Then we looked at its geometry, dimensional, and tolerance. Then we characterized microstructure mechanical property to end up with the final component. The next slide, please. This is something that is fairly rare. Only a few people in the world are working on this. With the 3D printing process, there's a possibility of texturing the microstructure. So you have an example here to go quickly on impellers for pumps. And depending on how you align the atoms during solidification, you can texture part with what we call in the jargon the 100, 110, and 111 orientation. And you can see on the right side of this graph of this slide, the different mechanical response that you have depending on the orientation that you do. So you can now start thinking with a fairly low cost to fabricate components that have a high texture and can give you specific properties that the conventional material cannot give you. And what you have on the left, on the bottom, is a response for corrosion. And you can see here again that if you tailor the way the atoms are put together, you can maximize corrosion resistance. So there's an opportunity here again to think of having material that are superior to the conventional wrought that are fabricated. The next one will be quite rapid. I just want to show you, next slide, yes. I just want to show you here the importance of the control of residual stress. So like welding, the development of residual stress is quite important during processing. And if you cannot control, you're going to go off the specification of geometry, dimensional, and tolerance. So I'm showing you on the example here, mainly focus on the center part, which is a diamond tube, which seems to be quite simple shape. It's a very tough shape to fabricate without distortion. So the example that you have on the left is what the conventional 3D printer are giving, the type of distortion that you can see from the map at the bottom. Once we apply the algorithm that we developed, you can see that the dimensional and tolerance was within 200 microns from the specs, which was quite nice. And now it can think of opening new geometries to fabricate. Just as a reminder, a hair of a human oscillate between 80 and 200 microns. So the part was quite precise in its fabrication. The next slide is to finish on the example is alloy development. So turbine tip repair for turbine tip repair is quite an important field. And with some sponsor, we've worked at developing new alloys that could have what we call, again, in the field, high gamma prime, so really high strength at high temperature. And we've developed a few alloy composition that can now be used just to refurbish the tip of the blades that you have once they are worn. So what you have here on those slides are a couple of results that we've obtained: extremely high mechanical properties at high temperature. The creep property is equivalent to a René 80, which is a standard alloy used for blade. And interestingly, if you look on the graph on the right, bottom right, the oxidation resistance of the new alloy that was developed is way superior to the René 80. So in terms of, so we can expect less damage for a part that has been repaired with this type of alloys. So these are 4 examples that we've worked with, among many others that we've worked with the group, with a few companies. And then a few things that I was asked to comment on will go quite the importance of the industry-university relationship. On my opinion, this is extremely important in the field of AM because it's a very new field in terms of adoption of the technology. So it really, really needs to de-risk the technology and to understand what's beyond so that people can use it and be certain of the properties and the reliability of the component that you're going to have. So we can demonstrate with those types of consortium, large bundle of people that AM is real. And that allow as well the development of supply chain pillar that are really important. It's really good to have a good design, a good demonstration that AM works, but we actually need to have the parts. And the last one that I have to comment, the next slide, please, is on the key element. And I think some of my previous collaborators talked on it. It's very important to talk the same language. And it's very important to come up with a problem-solving mindset. Yes, of course, all of this is leveraged with insert money or other funding industry. So paper have to be written, but that should not be the primary goal. We should be there to solve the problem, work with the company, and that's going to allow us to understand better the field and propose a better solution. And finally, timing is everything. So deliver on time, high quality results. So in a nutshell, if you can move to the next slide as a conclusion, additive manufacturing is becoming a key player in many industries. We're going to be seeing more and more of those parts in vertical lift system that you have for helicopter, drones, etc. And we're going to see this even amplified when we're going to have to work with light wing vehicle for hybrid and electrical model. So thank you very much, and I'll be pleased to entertain questions.
Thank you very much, Mathieu. So we covered a lot of subjects in such a short time. I think we covered the 3 important aspects that I wanted to talk about, which is that the industry and universities collaboration is mainly, in my opinion, about 3 things. It's either to analyze subjects like we've seen in Stéphane's presentation, to try to figure out how the sound work, how it is propagated. With Eric's presentation, we saw really what is a test campaign using the university, but with a collaboration from the industry. And finally, we covered the subject of developing new materials, manufacturing methods, which are all very important things that are key for the development of new technologies. So we have a few minutes for questions. I'll start with a question that we have for Eric. You're working with various industries on icing, including Hydro-Québec. Is working with aerospace any different?
It depends. We work on different project configurations. So from a completely private funding project to grants with public financement. So this change a little bit the kind of data you're gonna get, the change also the scope of the studies. So sometimes you're gonna be more of a test campaign, preliminary results to show some effects. Sometimes you're gonna go deeper into the theory behind it with PhD students and stuff like that. So I will say that it depends on the type of collaboration you get, and you decide with the clients either with full R&D 3 or 5 year projects or more of a test campaign of 1 to 2 years. That's what mostly going to change in what we're going to do.
Okay, and another question for you, Eric. How do you see working with the industries right now? You've shown rotor icing of rotor that are quite small, but do you see a way that the industry and the universities come together to be able to perform full-scale icing tests in the controlled environment, for example, on helicopters?
That is a very good question. Something that we have discussed with some partners. We have run a lot of smaller scale testing, and we are increasing the scale each time we go to a new project. We also have a project now that we include a full tail rotor in a cold room, but the RPM speed will be limited to the to lower RPMs for now, but already the scale is full for a full tail rotor scaling. So it's getting there. We would like to go there very much, and we are constantly discussing this with the partners.
Great. So I assume the answer would be it needs a lot of cash.
That's one of the issue. There's also safety concern of high-speed rotations, larger items in cold rooms, and the shedding of bigger pieces of ice and stuff like that. But yeah, that's one of the main concerns.
Okay, thank you. Our next question, very interesting question for Stéphane. You talked about drones a bit and the urban uses of Rotorcraft. What should the industry be focusing on to reduce noise? And do you think there's a big noise reduction technology that could be coming in the next few years?
I think we are still at the stage where we are, I think, testing different systems. So it's still, I would say, going in many directions. We've seen some of the problems we may have actually with the UAM, and it's a crucial, I would say, problem. Noise. It's we have safety and noise basically. There is no miracle, I would say. You have to reduce, as I showed, like the tip region is one problem. You may want to push basically the vortices away from the next blade, things like that. But otherwise, there are also tests with serration to optimize, to help it. But I'm not sure that it will basically just solve the problem itself. Okay, it will be there, and we have to combine, I think, different approaches. But I don't see any, I would say, miracle there.
So a lot of work for you in the next few years to try to get there. And finally,
there is also distributed, I would say, propulsion. That's another idea where you can split, so and then combine. So it's possible that you have a solution there.
Okay.
Sorry.
Thank you very much. And finally, for the time that we have left, a question for Mathieu. Right now, additive manufacturing of metal is more for smaller parts. Do you see in the next few years an increase in build size, and would it be economically viable in the future?
Well, this is an interesting question. There's larger and larger printer that exists. There's different technologies that can make meter size parts. If you think of the DP approach, but these days the powder bed are in the range of 1 meter that we can produce. So slowly, the size of the part is increasing. And if you just do an analogy with other field, the largest monolithic component that we produce and we typically use is an engine block that is casted. So that gives you the size of a part that we typically use without a weld or without an assembly. So that gives you a size to start with, and then we can grow with the availability of the new types of printer, definitely.
Okay, thank you. And also, since you've been working on additive manufacturing for quite a few years now, do you find it difficult to introduce new material in technologies in industries with a high degree of conservatism like the aerospace? Have you seen any challenges because of that?
There's many challenges, and I think you touch it right away. So 3D printing is a millions of weld, and welding doesn't like high strength material, and aerospace like high strength material. So yes, it's really challenging. And the question is, we are opening more and more variety of alloys year after year. The question becomes, what will be their reliability? And that's going to take, again, a couple of years to solve. Yes, it's possible to do it in a lab. Can we do it year-long in an industrial setting? There's more and more data on this that needs to come. But as I said, the field is really emerging in terms of commercial adoption. So it's going to take a couple of years before we can solve this issue. Let's call it solve this issue of those high-strength new materials.
Sounds good. So both of you three, all of you three have a lot of work for the next few years. That sounds good. So thank you very much for attending this webinar. I'm also very, very grateful to our three speakers who took the time today to share their experience and talk about some of their projects. I wish you all a great success in your work. And I personally will be very happy to continue working with you three on projects for the future of vertical lift. So thanks once again, and have a good day.
Thanks, Maxime. Bye-bye.